Good afternoon, everybody. Today I'm going to share with you some information about fast yet low power RISC-V core IP. This is the contents, the cores lineup information with you. There are some new cores I'd like to disclose. This is the first ever quarter we have so many new products to announce or to release. Today I'm going to share information with 6 cores here, from Cache-Coherent Multicores to Linux and DSP FPU-based cores, then fast compact cores with FPU DSP feature, then a slim and efficient core, which is entry level. Andes already moved almost all research and development resources to this area. So we built up a RISC-V product portfolio. We are focused on most of all embedded CPU. But also we have a subsystem IP, which we sometimes call them platform IP. That's the IP part. I will focus more on the RISC-V cores. With RISC-V, there's some characteristics significant. For example, it's simple, it is modularized, it allows you to add your own extension or your customized instructions. So taking this feature, Andes also built its own secret sauce on RISC-V, which we call it the Andes extensions. That make the core run faster and perform better and consume less power. What are they? Secret sauce includes baseline ISA extensions from Andes, custom extension framework for domain-specific architecture, some other extension we can state one by one. For example, we have proprietary ISA that can make memory access faster, and we can make branches faster, and we can have more compact code on top of RISC-V compressed instructions. We have powerful tools to make you be able to add custom extension on top of RISC-V cores. Also, we have a platform level interrupt controller extensions, which was donated to a RISC-V cluster. It comes with a vectored dispatch, priority-based preemption, and save more than 50% of instructions for interrupt. We have our own cache support mechanism, stack protection mechanism, power down, wake up mechanism, power management, which we call the power break mechanism, so that we believe it is the best extensions to RISC-V. Based on that, we announced a new entry-level core N22, the first member of 22 series in this core here. It is a 2-stage pipeline core, single issue. Also support physical memory protection. The instruction set is based on RISC-V 32, RV32 IMC, or RV32 EMC. Some of its features include, for interface, AHB light bus interface unit is there. Also a fast I/O interface is there. Physical memory protection up to 16 entries. It comes with machine mode and machine and user mode. We support fast multiplier, or you can choose slower but very small multiplier. It supports branch prediction, static or dynamic ones. For interrupt, it can have wait for event, wait for interrupt, or wait for event interrupt.
Can you ask what's the difference?
You know, it's used for microcontroller type of interrupt, which you have only one interrupt, a single input. Or if you connect to a larger system, like you have many small core to organize a bigger system, Then waiting for event, it's like from other CPU generate an event and then come in input a interrupt to this core.
I see. So basically it's inter-processor communication.
Yeah, right. Yeah.
The interrupt is ready for the sensors or peripherals.
Yeah. We do fast but still low power core. In 28 nanometers process, this two-stage pipeline core can run up to 800 megahertz in worst case condition. And yet it's only less than 15K gates logic. We always supply sub-core RTL. Customer can easily use it to synthesize and do SoC embedded design. The performance of this core is quite good. In terms of core mark, it runs to 3.97 core mark per megahertz. For dry-stone MIPS, it's 1.8 dry-stone MIPS per megahertz. Comparing to M3 and M0 Plus, the benchmarks data we can get from website, in similar segment configuration, we can run 19% better in core mark for M3 comparison or 26% better comparing to M0 Plus. And then 44% if comparing dry-stone MIPS in comparing M3, 17% comparing M0 Plus. For code size for M0 Plus, it's about the same, but if running a CSIB code size, it's 13% less. Now I'm going to switch a subject to DSP feature. Andes is the chair of RISC-V P extension, which is the SIMD DSP task group. We are the first to integrate such a P extension to a RISC-V core. In this page, I'd like to show that running for 32-bit RISC-V instruction set P extension and running for 64-bit, combining some different kind of categories in DSP functions. The Speedup, averagely for 32-bit, it can go up to 1.9 times. And maximum, it can go up 5.7 times. For 64-bit, averagely, it can be overall 3.6 times better. For max, it can go up to 12.2 times. Benefit of the DSP? Yeah, of course, if you add the DSP to a core, then you can process data like digital signals, which might be from sensors, from audio, video, and images. So such kind of a speed up will make the processing of voice recognition or video recognition or simply image processing much faster. We had some experiment on various applications such as this is kind of face detection, such as image classification, or voice codec application, MP3 decode. They can have different kinds of speed up. So we kind of add this core to our product portfolio this quarter. For the entry-level core, I mentioned that the N22 and this core D25, they are available now. We put this DSP coming from our existing core D10 and D15, which was designed 3 to 5 years ago, and we donated it to RISC-V community to be the base of a P extension ISA. And this ISA is still under review of this task group. We expect to make it a standard very soon, but we now launch this product with a P extension draft. So there are some details. One big advantage is that we use a RISC-V defined general purpose register as the register for this DSP. So there's no additional registers that save the logic and size of the core. And it supports various SIMD features like saturation, rounding, fixed point, and integer data type, SIMD instructions, more complex DSP instructions. Also, we upgrade to existing products that we launched 2018. Now, in this quarter, we upgrade them with the P extension. So they are A25 and the AX25. The difference between A25 and AX25 is AX25 means 64-bit, and the A25 is 32-bit. So now that AX25 and the A25 all features DSP now. That's for DSP. Then I'm going to switch my subject to a multi-core products offering. We announced the 2 cache-coherent multi-core also this quarter. However, the availability will be by second quarter. A25MP and the AX25MP. Again, X means 64-bit. MP means a symmetric Linux-capable multi-core. For this core, it can be configured as 2 cores or 4 cores multi-core CPU cluster. The instruction set is based on RISC-V IMC ACFD, which means floating point and the double precision APU both are supported. And P extension also supported. We have our own cache-coherent unit, ACU, which features MESI protocol for cache coherence. In terms of bus interface, let's have a look at this chart. For this block diagram, we can see the bus master interface comes with AXI 128-bit. We have I/O coherence slave port for it. It's also AXI. And then for each core, we can have a slave port. So each core can link to its local memory and iCache, Dcache. Then talking about the cache controller, let me add that for this multi-core, it can be configured as 1, 2, 4 cores. The default is a level 1 local memory. However, the level 2 cache controller is optional. So for this optional level 2 cache controller, the features are like it has up to 2 megabyte, 32-byte line, and a 16-way pseudo random replacement and write-back mode. The error correction is ECC error protection. The mechanism is SECDED. It also features prefetching with a load store, because sometimes there could be a cache miss. So when there's cache miss, the unit will track 8 different address sequences and prefetch up to 8 lines for making the performance maintaining still there. The other, for instruction prefetch, it also like this. After a level 2 miss, it can prefetch up to 3 lines. So for instruction and the data, they have both prefetch feature. And again, we add the platform level interrupt to this multi-core product. This is a SoC example. If you apply kind of a master-slave architecture to a SoC, which means, for example, if you have an application that requires Linux symmetric multiprocessing application, then you apply X25MP with 2 cores or 4 cores. And like I mentioned, we supply kind of a CPU subsystem. So there's pre-configured subsystem can be supplied from Andes. It comes with the core, the platform level interrupt, some debug module, and XI bus decoder. Then we have a design example, makes you to have a unicore with a DSP to do system control or acceleration control as this one. So overall, the SoC can be architected as a master-slave kind of product. Now I'm going to switch my subject to custom instruction. Even David Patterson, he also mentioned this terminology, DSA, a domain-specific architecture. One significant example is artificial intelligence, AI. So for that kind of application, RISC-V is good for building up AR, VR, AI kind of different architecture, especially when you have your proprietary knowledge that you like to add your own instruction to the RISC-V-based core. And this supply a very good environment to this. Because we have various CPUs based on RISC-V, so you can take one of them, like I pointed out, and add instruction set by yourself. And I'm going to talk about that, how. But before that, let me talk about the benefit of this environment. Engineer could be able to add instruction set to a core. However, they always be afraid of the consequent difficulties, such as compiler, such as software development, such as debug and verification. In this environment we provide, users only focus on the instruction semantics, not the hardware, including CPU pipeline and the RTL generating, and then including the software part, such as the environment for verification, for development tool, and including the compiler. So the housekeeping tasks are offloaded to EDA type of a tool provided. For example, the opcode selection, instruction decoding, operand mapping, access, update, and the dependence checking. These are kind of an easier design if you run our Copilot tool. It's like we can unlock the RISC-V potential for DSA. You can do it by leveraging Copilot, or Andes could provide a professional service to help with that. And this is the idea, the broad diagram describing what I just talked about. For engineer, he only focus on very high-level languages, kind of instruction semantic creating, and leave the housekeeping like RTL generation, instruction set simulation, and extended tool like a compiler, assembler, disassembler, debugger, and tool chains. All these will be generated automatically. And there is one bonus, which is the automated environment for cross-checking. I'm going to use this table to conclude points I highlighted today. We announced 6 new products or upgrade this quarter: N22, D25F with DSP, A25 upgraded to come with DSP. For A25MP and AX25MP, 4-cores multiprocessor products, they come with a Macy protocol cache-coherent unit. They also come with a DSP feature added. And that's most contents I covered. So in summary, today I talked less in a software type of ecosystem. Welcome to take a look at our website for that. In terms of the whole RISC-V community's ecosystem, it is in faster expansion now. And in Andes, we put our focus and almost all the resources to develop processor IP for RISC-V now. We like to be a pure player for IP provider on RISC-V core. And we tend to be trusted computing expert to help shipping millions of RISC-V-based SoC in the future, like we already helped to shipping billions of Andes' own architecture-based SoC in the past. The point is, Andes is committed to be your reliable RISC-V IP provider. That is my presentation. Thank you.